and we can go ahead and start with the first tutor.
Hi, okay, I'm going to share my screen. Okay, so I'm going to be talking about the statistical and thermodynamic definition of entropy and just kind of explaining how they differ and how they're the same. And all of the information will be from the textbook and the lecture slides if you need to reference anything. Okay, so first off, we're going to start by defining it in both ways. So the statistical definition of entropy is just S equals KB ln W, which is multiplicity. And one unique thing about this is it uses the Boltzmann constant as a proportionality constant. And also it makes like intuitive sense that the entropy would relate to the number of possible states. So it's kind of easy to understand. And then the thermodynamic definition is that delta S equals Q reversible divided by T. This is like the historically older definition, and it's easier to determine, although it doesn't necessarily make as much intuitive sense in your head. So just briefly, we're going to go over the thermodynamic because we've already spent some time with it. But so it's delta S equals QF over T. And one question you would have is how do we use this? And for an ideal gas, you can remember that Q reversible equals negative work reversible, which equals nRT ln of V2 over V1. So it follows that delta S equals N times R ln V2 over V1. But the statistical definition isn't as straightforward, unlike the thermodynamic definition. So you need to spend a little time trying to understand how to actually utilize it, even though it may make sense. So before we do this, you kind of have to understand the spatial distribution of molecules. So two important terms to understand when defining this is the state and the microstate. So if you can take 20 to 30 seconds and just think about what a state is and what a microstate is and how are they different, especially with regards to entropy, do that. And then you can either send something in the chat or unmute yourself. I'll try and get access to the chat. But yeah, so just spend 20 seconds thinking about that. So does anyone want to answer or send something in the chat? If not, I can just go.
So I guess for state, state is like the temperature or the volume or just the environment of that the gas is in, but the microstate is a snapshot of the state of the molecules moving around. So it's a single snapshot of the specific state at a specific time.
Yeah, perfect. So the state of the system is characterized by the global properties of the system, like Daniel was saying, such as temperature, pressure, and number of molecules. Whereas a microstate is each particular spatial configuration, like a snapshot in time, or distribution of atoms and energy levels that's consistent with the definition of the overall state. So there'll be many microstates per system. So here's kind of a visualization. So as you can see, state one, the atoms can be anywhere in the box, where it's shaded tan, but in state two, the atoms can only be in the left-hand side of the box. So this contrasts with kind of the idea of microstate. Although these pictures look pretty similar, they're different because these are two instantaneous snapshots of a moment in the time of a moment in time of one system. And so theoretically, the atoms can be anywhere within the state, but in microstate 2, they've chosen to just be on the left side. And then how do we count them? So the formula is W equals, or multiplicity number of states equals M factorial divided by N factorial times M minus N factorial. And M is the number of grid boxes, or more practically the spaces that an individual molecule can take up. And M can be arbitrary if it's large, because we'll mainly be using it in comparison to another system defined by the same sort of restraints. And it will be proportional to the volume. And n is just the number of molecules. So this is from the lecture slides, but it's an analogy to coin flips. So using the equation outlined above, try and determine the multiplicity of the system or how many ways you can get to roll or toss two heads in 10 coin tosses. So take about 30 seconds to do this, and then you don't need to solve for the actual numbers, but just try and figure out what m and n is and then input them into the equation. And then you can send it in the chat or say something if you want, but yeah.
Is it 10 factorial over 8 factorial times 2 factorial?
Yeah, so m can be 10 and then n is 2. And so that would give you 10 factorial divided by 8 factorial times 2 factorial. And it's important to notice that you could do this with n equaling 8 as well. It would give you the same answer because it's just like two sides of the same problem. Awesome. So now we're going to make it like a little more complicated and more realistic. So it's the same question as before, basically, but if we set WB equal to m factorial divided by n factorial times m minus n factorial, what will WA equal in terms of n and m? So again, like take a little bit to think about this, and then you can send it in the chat again or say it loud. And if you need a hint, pay attention to the volume. And
so would it be that m is m divided by 2 and the number of atoms stays the same, so n is the same?
Yeah, so you can assume, I guess I should have said it, but that A is half the volume. And so this will be the answer where m will just become m divided by 2 because m is proportional to volume. And so this, since A has half of the volume of B, m will be half of what it originally was. And then you just plug that into the equation. But since the number of molecules is the same, n stays the same. Okay, and now we're going to talk a little bit about Stirling's approximation because it's going to be useful for like the rest of the presentation. But basically, it's just that ln of n factorial is approximately n ln n minus n. And this holds true for just large integers. So make sure that you're only using it if you're actually using large integers of n. For this approximation, you can use it and to determine that w equals m factorial divided by n factorial times m minus n factorial is actually the same as ln of w equals n times ln of m divided by n. If you want to like look at the derivation, it's in the lecture notes in the textbook. And this is only true when m and n are very large and m is much greater than n. So if you don't necessarily need to like memorize the derivation, but you should be able to apply Stirling's approximation to derive this equation. So that's just repeating it. And so again, m is the number of grid boxes, and then m is equivalent to alpha, which is a scale factor, times the volume. So just another way you can write this is ln w equals n times ln alpha v divided by n. So now we're going to talk about change in entropy and like how it's actually useful. So S equals kV ln W, which is just the equation from earlier that we're given. And so delta S will equal kV times ln of WB minus kV ln of WA. So that's just figuring out the change in entropy by subtracting the entropy of one state from another. And then as you do like just some math, you can pretty easily substitute in order to, and then substitute like the volume approximation in order to find this in terms of volume. And so it's n times ln of BB over BA, which will equivalent to S2 minus S1 over KB, or delta S over KB equals n times ln of V2 over V1. So n in this equation is the number of atoms, and n equals n times Avogadro's number. So when you input, or equals moles times Avogadro's number. And so if you input the little n times Na into the equation, you can then replace Na times Kb with R, because that's just what it equals. And so you get delta S equals NR ln V2 over V1, which is the same as the thermodynamic definition that we referred to earlier on. So they're actually equal, but you can use them for different things and like understand them in different ways. So that's the end of the presentation. Does anyone have any questions or like want to see any slides again? Okay, if not, I'll just give it over to the next tutor. Thanks.
Okay, so today I'll be going on just a few topics that are mentioned here in the title. So I'll be talking about the relationship between heat transfer and entropy, a little bit of binomial statistics, and I'll also cover the second law of thermodynamics. So with that, I'm just going to get started with the presentation. So first, here's sort of like a motivating example. So far, you've seen in class when you look at isothermal expansion specifically for the system in which you have gas and you have a cylinder. If you were to place it in a heat bath like this, where you have a constant flux of heat because the bath is kept at a constant temperature, you notice that even though you're at isothermal expansion, the gas still expands spontaneously and does work on the cylinder. And if you recall, there's some equations that are governing both the internal energy of the gas in the cylinder and also heat flow. So what we can see here is that if the internal energy of the system is represented by this, because as is stated in the name of isothermal expansion, the change in temperature is actually 0. So what we see is that although the change in the energy of the system is 0, you still have a spontaneous process, which is kind of intriguing because despite there not really being any energy gain for gas expansion to occur, we see that this expansion is still a spontaneous process. And so after observing this, we wonder, are we missing some type of variable that could be accounting for this process? And in class, you've probably discussed that entropy is one thing that causes this to happen, because in our delta U equation here, we're not accounting for entropy, so we're not able to see the full picture in terms of why something might be a spontaneous process. And so I'll explore this a little bit more in the upcoming slides, and also when I talk about the second law of thermodynamics. But really quickly before I get to that, just recall that in this system, because your change in system energy is 0, we have that the reversible work that's done by the gas is equal to the amount of heat that's reversibly added to the system. And also recall that for an ideal gas that's expanding and doing work on a cylinder, the work that is done is given by this expression. And in case if you're wondering where this came from, recall that work is defined as P external times change in volume. And so then if you apply the ideal gas law and substitute that in for P, you can rewrite P as nRT divided by V. And if you take the integral of that from V1 to V2, you'll get this expression here. And this should also be in your textbook and your notes, so you can refer to that if you're interested in the derivation of where this comes from. But once we've established that, now we can look at how entropy changes within the cylinder system that we were talking about. So in the previous slide, I mentioned something that was just touching upon how heat flow can influence entropy. But first, I'll start with the probabilistic definition of entropy that deals with microstates. So here, just on the bottom right, note that there are some useful log properties that most of you probably know by now, but they're just there for reference. So now if we're considering the system in which you just had the same number of n atoms in either of these states, where in one case the total volume is VA and the other one's VB, if we want to calculate the change in entropy, what we first have to do is consider the number of microstates, which is given by W. And recall that if you are using the Stirling approximation, you can rewrite W as this expression. And in order for this to be true, you need to have a very large n, because as you'll remember, the Stirling's approximation gets better as n increases. And also you need to have m being much, much larger than n. Additionally, we can observe that m is proportional to volume because m is just the number of empty grid boxes. So as you have more and more volume, you should have more empty grid boxes. So we can say that m is obeying this proportional relationship. And then in calculating the change in entropy, we just do KB ln WB minus KB ln WA, because this gives the first term over here gives the total entropy of state B, and this term over here gives the total entropy of state A. And if we take the difference and apply log rules and make substitutions like this, you will end up with this expression here. And just as a note on converting between this expression on the left and the right, just note that n is the total number of molecules, which could be any number of moles. And just to getting from n times kb to the number of moles times r, this is just the definition of the gas constant r, in case you're wondering. And so this expression is actually pretty important because, as you'll recall from the previous slide, the way that we had defined the change in heat from the system in terms of if this is isothermal expansion, the amount of heat that's being added to the system is very similar to this. So if you'll recall, Q reversible divided by T is actually given by this expression. And so this is pretty significant for us because this shows us that if we consider the heat flow in an isothermal process, it's actually just equivalent to the change in entropy as long as you divide the heat flow divided by T. So this basically shows us that there's an equivalent relationship between the probabilistic way of defining entropy and also the thermodynamic definition of entropy. Does anyone have any questions so far? Okay. So with that said, now we can go on to discussing the second law of thermodynamics. So far, our intuition about entropy and the second law of thermodynamics has kind of told us that even if we have a system in which the total enthalpy change is 0, if there's at least a gain in entropy, then the system could favor a spontaneous process occurring. Now to kind of tackle that in a little bit more rigorous way, these two quotes are both from the textbook, and these are just different expressions for what the second law of thermodynamics says. So the first one is that the combined entropy of the system and the surroundings always increases for spontaneous processes. And this is kind of in line with their intuition. Like if we're increasing the entropy, then the process should be spontaneous. And additionally, the system and its surroundings achieves maximum entropy at equilibrium. And so with this statement here, which is just a restatement of the second law, we can arrive at this expression because the entropy of the system and the entropy of the surroundings should give the maximum entropy. And then furthermore, if you take the derivative of this, you should get 0. Here is a graph that should help you visualize this a little bit. So on the x-axis here, you have the internal energy of the system, and on the y-axis, you have the total entropy. And you'll note that when you've achieved equilibrium, the derivative at that point should be 0 because this is the maximum. And you'll deal with this equation and a little bit more of sort of the rigorous mathematical workings of this when you look at the proof for delta G, which is free energy, but that's coming up in future lectures. Hopefully this sort of gives you just like a taste of what's to come. But at least practically for our purposes now, when we're thinking about the second law, really what we want to think about is that entropy is just another way to kind of determine whether or not a process will be spontaneous, because previously we were just looking at energy changes to determine if something is spontaneous, but now we know that even if the delta U for a system is 0, an increase in entropy can still make it spontaneous. Does anyone have any questions so far? Okay, so then with that, I'm just going to switch gears really quickly and now move on to binomial statistics. And this is where Pascal's triangle becomes pretty important, and it's a very useful tool for dealing with problems of binomial statistics. So you should have seen this in lecture. And so just to show you how to use this, I'm going to go through an example calculation. So for instance, if we want to ask ourselves, how many ways are there to get 8 heads and 2 tails if you flip a coin 10 times? The way that we can use Pascal's triangle is to first recognize that, okay, if we're flipping a coin 10 times, then that refers to the number of trials. So we will look at just this row here, which is 10, corresponding to the number of trials. And then we'll ask ourselves, okay, if we have 8 heads and 2 tails, this is the same as either looking at, so this is 0 indexed. So I could either look at 0, 1, 2, the second element here, or I could look at the 8th element to get the multiplicity. In this case, we'll just think about it in terms of 2 tails. So 0, 1, 2, 45 is our multiplicity based on Pascal's triangle. And then that gives us the answer, 45, which is essentially 10 choose 2. So if you wanted to do it using multiplicity as defined using factorials, you could do that as well. It's equivalent. But a more interesting question, I think, is what is the probability of an event like this occurring? So we just solve for the fact that there are 45 ways to rearrange a combination of 8 heads and 2 tails, but how likely is this actually to happen? And so when we're considering the probability, it's not enough for us to just talk about the multiplicity. We also need to think about the actual likelihood of this particular arrangement happening. And the way that we can calculate that is by first saying, okay, so in order for us to get 8 heads and 2 tails, what we would have to do is get 8 heads and then also 2 tails. And so we would need the probability of heads times that 7 more times, so a total of 8 for the probability of heads, and then for the probability of tails, that would be squared. Of course, because we're assuming that this is a fair point here, we can just plug in 1/2 for both. And additionally, we can multiply by the multiplicity here, and in this case, the multiplicity is 45, and that gives you that the probability of seeing this particular arrangement is about 4.4%. And so this was just sort of the walkthrough when we were looking at flipping coins. But the way that you might apply this in this class is by looking at binding sites in an enzyme. And this is the question that I've written on the worksheet. And here I'll just go through a walkthrough of how this will work. So here the question is, suppose there's an enzyme with 4 binding sites and that the probability of a ligand binding is 0.25. What is the probability of 3 of these binding sites being occupied? And so in working through this problem, this is very similar to what was done on the last slide, in which you need to consider first the multiplicity of an event like this happening, and then also incorporate the likelihoods into calculating your probability. So does anyone want to just mute themselves and tell me what the multiplicity is of 4 binding sites and 3 of them being occupied?
So would the multiplicity be according to the Pascal's triangle 4?
Right, it would be 4. And the way that you can see this through the Pascal's triangle is by looking at 4 for a number of trials. And then since 3 binding sites are occupied, we look here. And remembering that this is 0 indexed, we go 0, 1, 2, 3, and we get 4. And if you want to think about this intuitively, you can also think of this as if you have an enzyme with 4 binding sites and 3 of them have to be full, you essentially get 1 choice for the empty binding site. And so essentially you have 4 ways to pick which of the binding sites is going to be empty. And so 4 corresponds to the multiplicity. And of course, if we have a ligand that's binding with probability 0.25, and we know that 3 binding events have to happen, this means that we have an event that has a probability of 0.25 times 0.25 times 0.25, and then times 0.75 because the last event is that the site is remaining empty. And so this is kind of just the explanation of what we just walked through here. And if you do the math, this also corresponds to about 4.7% for the probability of observing something like this happening. Any questions so far? Okay, and so then really quickly, I just want to touch on 2 important properties of entropy that you might find useful in homework tests and just for conceptual understanding. And the first is that the idea that entropy is additive. And so there's a very important caveat here when we're discussing if this is additive. We're assuming that both system A and B are independent. And in the case that they are independent, we can show that the multiplicity of the combined system is actually just the sum of the entropies of both. And so first, let's try to calculate the multiplicity. If we're considering the multiplicity, we can imagine that for every single microstate that system A is, so if we froze system A in a particular microstate, system B could be in any other microstate in that snapshot. So I think there's this one figure in this book that does a really good job of visualizing this. So if you have system A and you just took a picture of it in microstate number 1, essentially system B could be in any of, let's say, 100 different microstates. And you could repeat the process for system 2 in a different microstate with 100 other microstates. And so hopefully what this shows you is that the total number of microstates when you have combined system A and B is essentially just the product. And then if you want to find the log of the multiplicity, then it's just the addition of the 2 logs. And then when you're calculating entropy, entropy is just KB ln this and then KB ln this. And so you get that the entropy is the sum. And so entropy is additive, assuming that these 2 things are independent. And the last note on entropy that I want to make is that entropy is an extensive property, which is also mentioned in your slides. And so before we talk about how to show this, just a quick definition of what an extensive property is versus an intensive property. So an intensive property is something that doesn't depend on the amount of something in a system. So for example, if I had just like a bunch of iron, like a sample of iron, the temperature of that sample does not depend on whether I have a gram or a kilogram. So temperature is an intensive property. Whereas if I was measuring the mass, that very much depends on whether I have a gram versus a kilogram. And then to show that entropy is an extensive property, what we can do is just double system A. So now we have double the number of empty boxes, double the number of molecules. And then if we calculate the entropy of this new system A prime, you work through the math, you see that you get 2 times the original entropy. And so again, remember that because we're applying Stirling's approximation to get a lot of these numbers, this calculation is only valid if we're assuming large M and large N, and also that M is much larger than N. Okay, so I think that's all I had for you today. Anyone have any questions?
Can you go back to one slide, please?
Sure, this one?
Oh, yes. Okay, thank you.
Hi, I have a question.
Yeah.
So when you say a combined system, do you mean both volume and number of molecules are both like combined? So the combined system has combined volume and combined number of molecules.
Right. Yeah, so I mean, if you were to like merge these two, then that's what I mean by combined. So yeah.
So when you have a system of like 20,000 molecules and it has the entropy of say S1, and you throw in another 20,000 molecules to that original system. And can I say the final entropy is 2S1, or it's not because the volume is not increased?
So I think that if you're referring to the question on the homework, the thing to remember for that one is that you have to consider both A molecules and B molecules. And so then that adds another layer of complexity. I think the tutors in the next session will probably cover that in detail, but I might be able to answer some questions in the chat later on. If you have them.
Thank you.
Any other questions? Okay, I'll stop my presentation and I'll just
for the extensive property. So when we
sure.
say entropy is an extensive property, and you know how we define the extensive property to be like how much it changes based on how much of the system there is. So would it be that entropy is an extensive property due to if volume changes? So like the extensive property itself is or because extensive property is defined as like how much of the system there is. So would that be the volume in this case?
Well, in this case, it was both volume and the number of molecules that were changed here. So here in this calculation, I doubled both M and N, and that's why you end up with an entropy that's twice what you originally had. But if you only doubled the volumes, so in this case, only doubling M, then your change in entropy would only be multiplied by a factor of ln2.
Okay, I see. So the extensive property is both the volume and the number of atoms in the system.
Right.
Got it. Thank you.
Okay, all right, so I'll answer any more questions in the chat, and I'll just give it off to the next tutor.
Okay. So I'm going to be going over the entropy of energy distributions. Energy distributions tells you the number of molecules in each energy level. So it tells you the total number in each level, and the identities or the order of the molecules don't matter within the energy level, but they do matter between the energy levels. At any instance, a particular molecule can be in any of the accessible energy levels within the bounds of the total energy of the system. So a molecule can't be in an energy level higher than the total energy because total energy is conserved, and that is our first law of thermodynamics. Okay, so for an example, here I have an energy distribution with the energy going up, 4 energy levels. I've labeled the populations of each level. So here we have 3, 3, 1, 1, and a total energy of 8. And I've also labeled the molecules with numbers. And so this is one microstate here that is possible. And if we just switch the order of 3, 4, 5 here, this is going to be the same microstate because the order within the energy level does not matter. So if we imagine that each energy level is a distinct box, so box 0, 1, 2, 3, and we just shuffle around the molecules in the box, that's still going to be the same microstate. And it's still the same energy, and so yeah, so nothing has changed here. And then But here, if we switch molecule 1 and molecule 2 between energy level 2 and 3, that is going to be a different microstate because now you've switched the molecules into different energy levels. And the same total energy still applies. So energy is conserved, and that's good. But if everything is the same here, except we move 4 and 5 to the third energy level, that means that energy is no longer conserved because now we have a total energy of 12. And this would be a possible microstate if we could input energy in some way, but if it's an isolated system and there's no incoming energy, this is not a possible microstate. And remember that our total energy equals the summation of the products of the number of molecules in the ith energy level, and then the energy of that level. So to calculate the multiplicity, the number of different arrangements of molecules possible among the energy levels, we're going to need to know the total number of molecules n, and that is equal to the sum of the number of molecules in each energy level. And so our equation is W equals n factorial, so number of ways of choosing n different molecules over the products of the factorials of the each population energy level number, so the number of ways of rearranging this number of molecules within their energy level. So, so you would have 3 factorial ways, for example, of arranging 3 molecules. And so you have to divide n factorial by all of these factorials. And this equation can also apply if you want to see the number of microstates corresponding to a particular distribution, because there are a lot of microstates that are consistent with a particular energy distribution. Are there any questions on any of this? Okay. So to calculate the multiplicity of different possible energy distributions to assess the probability of obtaining a particular energy distribution relative to that of another energy distribution, and the largest multiplicity situation is going to be most likely what you're going to see. So here I've drawn 3 different energy distributions for a system with 3 total molecules and a total energy of 3. If we look at the first one here, we can have all 3 molecules in one energy level, and this is going to have a multiplicity of 1 because there's only one way to get this microstate. If we have a different configuration with a multiplicity of 3, because you can have 2 molecules in the 0 energy level, but you have 3 ways to choose the molecule that's going to have 3 units of energy. And over here, you have 6 different possibilities because you can choose, because you have the 3 molecules and 3 different energy levels. And so that's 3 factorial over 3 1 factorials because you have each one in one energy level singularly. And so the most likely thing to happen is what you're likely to see. And so here, this would be this. So you'd most likely to see one of these, but in a system like this, where there's such a small number of molecules, you're actually pretty likely to see these 2 because this is going to be 4 out of 10. So these 2. And this is 6 out of 10. But if you have many molecules and a lot of energy levels, you can see that this calculation for the multiplicity can get very tedious. And so if you take this equation from before and you apply Stirling's approximation, when you have a very large number of molecules, you get the probabilistic definition of entropy. So all you need to know is your total number of molecules, and then you need to know the fractional occupancy, which is the number of molecules in each energy level divided by the total, and the probabilities all have to equal 1. So yeah, when you can use this equation, it gets a lot easier to calculate, so you don't have to go through this calculation with a lot of large numbers. Are there any questions?
The diagram, like to the very left in purple, where did the 1 factorial come from?
Oh, yeah,
on the
okay.
denominator.
Yeah, so you could say 0 factorial too, which is which equals 1 factorial, but so the 3 is from these, and then this is just I mean, maybe I should have written 0, but yeah, but it equals the same thing.
Okay, thank you.
Yeah. Okay, if there are no other questions, I can pass it to the next tutor.
Can I see the first paper? Sorry, at the
Yeah.
bottom.
And I'll post these too after
Oh.
this.
At the bottom.
Oh, sorry.
Sorry. Okay, thank you.
Okay.
All right, everyone. So we will wrap up today's session by talking more about the probabilistic definition of entropy. Oh boy, I already skipped this. All right. So let's first go over what the equation is, which is written down here. You have your entropy equal to negative n, which is the total number of molecules in your system, times your Boltzmann constant, Kb, times the sum of this fractional occupancy times its natural log. We'll go over that in a bit, but as Ryan was talking about, basically, you can use this equation, or we'd prefer to use this equation, when the number of molecules in the system are very large. It's easier to use than this basic equation because with this one, you'd have to account for a lot, each individual molecule. It'll be very tedious and just won't be worth your time. So let's go over what fractional occupancy is. Again, it's the probability that a molecule is found at some ith energy level, basically the proportion of number of molecules in that energy level to the total number of molecules, n sub I to n. So an important thing to know is that these are probabilities, or they are proportions of the total number of molecules. So all of these fractional occupancies need to add up to 1. And we call that normalized. So because those all add up to 1, that's where we get our negative sign from. So if they add up to 1, p sub I will always be less than 1 because it's a decimal, right? If you have half, it'll be 0.5. So when you take the natural log of something that's less than 1, it has to be a negative number. So that's where we get our negative sign, because when we plug into this, we'll get a negative value out of this term, the sum. So we have the negative sign here to account for that, make it positive, such that our entropy is always positive. And we'll see that you get that negative sign out of the derivation, the conversion. And I won't go through the whole derivation here, but it's good if you can look on page 351 of your textbook and just understand how you get from this equation to the probabilistic one. But basically, we'll take this equation and we'll be substituting in for LNW, your multiplicity. As Ryan talked about before, this is one way to write your multiplicity, n factorial, total n, divided by the number of molecules in the first energy level, factorial, second, et cetera, et cetera. So we can use Stirling's approximation to get an equation to simplify all of these factorials. We'll raise these to the e power. And from there, you'll just do some algebra. And basically, you'll get an equation for n factorial, n1 factorial, et cetera. Plug that in and simplify. And as you go through the algebra, you'll end up with the probabilistic definition. Just wanted to make sure you know you'll be using Stirling's approximation for that. So, and then just for using the equation, it's pretty straightforward, plug in.
You just need to make sure you calculate the fractional occupancy, divide the number of molecules in each level by the total number of molecules. And the good check to make sure you didn't mess up is that all of those fractional occupancies should add up to 1. So if you ever feel that you may have, dropped a number here or there, just make sure they add up to 1. And again, you could do the calculation with the S equals KB, L, and W, but that would take a lot longer. And your calculator may not be able to handle that. So, and as a note, the more energy levels occupied, the greater the entropy. So from there, something I want to talk about is units, because I know in this class, when I took it, my friends and I were very confused with what units to use, how to convert between them. So I just want to go over this real quick. Hopefully this makes sense. And hopefully I put down the right thing on my slide. So let's first start basic. So we're looking at this equation and this equation. If you just plug straight in, that would give you entropy in joules per Kelvin or kilojoules per Kelvin, whatever you want. That is the entropy for however many molecules you have in the system. So if you had 10 molecules in the system and you did the multiplicity and plugged into this, you get an entropy value for those 10 molecules for that system. Now, normally though, we're not interested in that. We're interested in entropy per molecule. That way we can compare between systems a lot better. So to do that, think of it as dividing this equation by n. So this is S divided by n, and here the n will cancel out, right? So you're just left with negative KB and then the sum. That is your entropy per molecule. However, confusing thing is a lot of the time people will just write it as joules per Kelvin. They won't do joules per Kelvin per molecule. So keep track and know what you're solving for. Are you solving for entropy per molecule or just general entropy? And another common question is, what is the entropy per mole? That's pretty basic when you go from entropy per molecule here. We multiply each side by Avogadro's number. So we have molecules in the denominator, multiplied by 6.02 to 10 to the 23rd molecules. Molecules cancel out, and now you have entropy per mole. And we see that here. And remember that your gas constant R is equal to Avogadro's number times Boltzmann constant. So you'll end up with this simplified equation using just the gas constant R. Does that make sense to everyone? Is there anything that was confusing? Any questions you have? Okay, so let's go to the problem. So you have a system with 23,000 molecules. Half the molecules are in the first energy level. 3/8 of the molecules are in the second level, and the rest are in the third. And calculate the total entropy for the 23,000 molecules and also the molar entropy. I'll just leave this up for, let's say, a minute or two. So just do this on your own, and then we'll go over the answer in a bit. And if you have any questions or ideas, feel free to unmute yourself. Sure.
When you say first energy level,
Yeah.
like maybe I'm getting mixed up, but like do we count that as like times like is that I don't know, is there a difference in whether or not it's in the first versus the third?
In terms of your math, no, because you just need to make sure you do fractional occupancy correctly.
Okay.
Yeah. So yeah, the actual like energy level won't necessarily apply. Just keep track of which one you're looking at.
Okay, thank you.
Mm-hmm. Okay. So how about we move on, we'll just go over the answer real quick. So the first question was calculate total entropy for the 23,000 molecules. So what that means is just the general equation, right? What's the entropy for the system? So you'll just plug straight in, so negative n 23,000 molecules times your Boltzmann constant, and these are the probabilities. Half is 0.5, 3/8 comes out to 0.375, and then if you add those up, 1 minus that answer, you'll get 0.125 for the rest. So just plug that into your calculator, solve, you get 3.09 times 10 to the negative 19th joules per Kelvin. So that was entropy for the system. Now going over the molar entropy, we can use our other equation, which is S is equal to negative R times the sum. So we'll have this stays the same, but now we can just multiply that by 8.314 joules per Kelvin per mole. Solve, we'll get 8.1 joules per Kelvin per mole. So it's pretty straightforward. You just got to keep track of your units and know which equation to use. I think that's the biggest thing people mix up during this unit. Any questions? All right. Okay, so I will stop. Message me in the chat if you want me to answer anything.
Okay.
Do you think you could show that the actual question again so I could take a picture of it?
Yeah, my bad. Oh, is this working? Sorry, something messed up. Give me 1 sec. There we go. And remember, this is also on the worksheet if you need it.
Oh, perfect. Thank you.
Yep.
Okay, well, if there are no further questions, I'm going to go ahead and stop the recording for the Wednesday concept session.